Welcome to the session on type systems. Our first talk will be Ellen, who will tell us about reference capabilities for flexible memory management.
All right. It's nice to be here. I'm Ellen. I'm coming to you here at Uppsala from Uppsala University in Sweden. I'm here to talk to you about reference capabilities for flexible memory management. Okay. I just want to say that this work is part of a larger project called Project Verona. It's a Microsoft project, and we have the end goal of creating a new programming language for cloud infrastructure. So let's get started. So in modern programming languages today, we seem to have this balance between memory safety on one hand and the amount of control a programmer gets with regards to memory management. So, for example, we take Java. Here, memory management happens completely automatically, which is, of course, very convenient for the programmer. They don't have to think about it. On the other hand, this lends itself very poorly to the kind of domain-specific optimizations that we all know and love. For example, if we have a resource that we know that we're not going to use anymore, we can't tell the system in some way that, okay, please free this resource immediately. We end up with a situation where this resource can take a considerable amount of time to actually get deallocated. On the other hand, we have languages like C++, where memory management happens completely in the programmer's control, which, of course, on one hand gives the programmer opportunity to make these kinds of optimizations, but we open a whole can of worms of introducing perhaps memory bugs in our program. Somewhere in the middle, we have languages like Rust, where the type system is able to reason about object lifetimes. So as long as we stick to the safe portions of Rust, we are sure that resources will be freed as soon as they're not used anymore. On the other hand, Rust kind of limits the expressibility or what data structures we can actually express, at least in the safe parts of the language. So what actually tends to happen is that people either need to write unsafe code themselves, or they need to at least use libraries that has this unsafe code. So what we wanted to do with this work was to kind of explore this space to try to keep the safety aspect of Java, but also give the programmer more control over memory management. So our system is called Regio, and we had set up a few goals for this system. First of all, we want the automatic memory management, since it's convenient and it ensures safety in our program. Second, we would like to have some kind of localized memory management, so that we are able to reason locally about what objects are used and what's not used, like currently in our program. This gives us a more predictable, or hopefully a more predictable, memory management overhead. Finally, we want a mix and match memory management strategy, so we're able to choose for a portion of the heap, for example, that it's supposed to be traced. Maybe another portion is supposed to be reference counted, and so on. Finally, we wanted our system to be as simple as possible to use, We've already seen with languages like Rust that people have difficulties when trying to learn them and reason about them because they're more complex than the earlier languages like C and Java and so on. And it's kind of a whole different dimension of reasoning. So we wanted to keep our type system as safe as possible. So what is Regio? We can imagine that we have some kind of heap. We have objects and references between them. The first restriction that we put in place is that we divide our heap into regions. So what this means is that each object is contained in exactly one region. Our second restriction is that we disallow certain shapes of this region graph. So all the regions form trees. So for example, here we could remove these two edges and end up with a tree-shaped region graph. Next up, as you can see here, we're kind of moving between the regions in last in, first out manner. So we basically have explicit open and exit operations, and we need to do this entering and exiting in a last in, first out manner. And this is to give access to give our program access to different parts of the heap. Depending on where we are in the heap right now, we get different access permissions instead as well. I'm going to explain these terms shortly, but we have the closed regions, which are the gray ones. We have the the active regions, which is the yellow one. And then finally the suspended regions, which are the red colored ones. And we do all this to enable this localized memory management. Finally, we enforce this statically using a reference capability system. So we basically tag each reference in our program with some additional information to allow us to reason about what relation, like the objects it points between has. All right. So closed regions are not part of this region stack that you saw earlier. This means that our program has no read or write permissions at all inside this region. We can still move the incoming pointer to this region around in our program, and we can also like drop it, for example. But we have no actual access permission inside the actual region. If we move on to the active region, it's on the top of the stack, of this region stack. And we have both read and write permissions. Specifically, we're allowed to allocate and deallocate memory freely, or the program has permission to do this. Next up is the suspended regions. So they are part of the region stack, but they're not on the top of the region stack. Here, the program has read permissions, and we are also able to alias from region frames higher up the stack. So for example, this reference here is permissible, but it's read only. So what do we actually get for all these, from imposing all of these restrictions? So when reasoning about liveness, we can see that for the suspended regions, liveness depends on the program frames and also, of course, the region local heap references and this incoming reference. But since the But since this region is read-only and these additional references are, like the red ones in this picture, are lifetime bounded, we can reason that we don't need to care about this region from a memory management perspective, since liveness won't be affected until we actually return to having this region as active. For the closed regions, we only have the local heap references and this incoming reference. Since the local heap is not mutable, the entire liveness situation boils down to this single incoming reference. Does that exist or not? Yes, and finally, liveness in the active region. Since we can mutate the region, we need active memory management. But basically, this boils down to a local property, liveness that is, because we only have the local program frame and everything else is kind of region local. So liveness is a region local property. So in the end, we get a situation where this active region basically decides where we are able to mutate. And we can move this kind of window of mutability around in the heap in this fashion, in this last in, first out fashion. And we get we can reason about only the currently active region when reasoning about mutable state and memory management. So to give you some idea of what we imagine that you could do with this, imagine that we have this large region with a lot of objects in it. And imagine that we need to kind of restrict the amount of memory management overhead and kind of try to keep it as low as possible. In this figure right here, you can see that we're able to split this big region up into several smaller regions. And then, depending on the region, the internal structure in the region, we as programmers can choose to have different memory management strategies in all of these. So for example, in one we could have tracing, in another one we could have reference counting. So to go back to the kind of goals of our system, we do get automatic memory management. We get localized memory management since each region is memory managed separately, and also we can reason about the overhead and a bound for the overhead in terms of the size of the currently active region. Finally, we get this mix and match property. Since we're able to choose freely whichever memory management strategy we have for each region. These properties basically boils down to this topology invariant that we have in our paper. I'm not gonna go through it in detail right now, but please read the paper if you're interested. So where does this leave us in terms of this whole picture that I showed earlier? We believe, at least, that we're able to kind of retain the safety properties of Java, for example, but still give more control to the actual programmer in terms of reasoning power and actual implementation level stuff. There is more stuff in the paper. For example, additional features like immutability and changing the region entry point. We have a description of the whole type system with reference capabilities, also comparisons with other systems, code examples, and finally a formalization and soundness proof. Furthermore, there's going to be a talk later today about a concurrency model that we have that we imagine can be combined together with Regio in order to get a very concurrent yes in order to enable a very concurrent program. All right, I think that's about it, so thank you for listening.
Okay, we have time for a couple of questions. If you have a question, please come up to one of the mics in the aisles here. So.
Hi, Jonathan Aldrich, Carnegie Mellon. Really interesting system. I think for me the biggest question is, is this practical for writing programs? Can we structure programs the way that we need to and make them work? Can you give me the intuition for why you believe this will be, will match the way people want to program?
We're working on an implementation right now, so hopefully we'll get something up and running that people can try to use. We do have some kind of code examples in the paper as well of a system that it's basically like a small server that handles requests. So I urge you to maybe read that if you're interested, and maybe we can talk a bit more later, if that's okay.
Thank you.
Okay, and one more question.
Is there any sort of region inference, or is it just the region management itself is a explicit operation?
At the moment, there is no region inference. No,
okay.
So you have to write out region creation explicitly.
Do you think that the region inference algorithm could be devised that's still compatible with the whole system in principle?
Yeah, definitely. That's for sure an interesting kind of future direction. I think.
Okay, thank you.
Okay, I'll have one more.
When you create a new object, does it go in the region you're currently executing into?
Yes, exactly. So when you allocate an object, it's always created in the currently active region.
So is there a way to move objects between regions, to merge regions?
Yes. No, sorry. So there is an operation, I think I forgot to mention it, to merge regions. So it's basically, if you have a closed region, you can merge that into the currently active one.
Okay, let's thank everyone again then.